So we want to do the open problem session. So we're filming this. I guess if anybody who shows up here, like, try to have this microphone. I'm gonna leave it here. Okay. So let me. So I wanted to, maybe start, and then maybe you can. Anyone who is interested can follow up. So I want to talk about the problem that I've been thinking about. It's a question of counting non-broken basis of a matrix. There is this thing that probably many of you don't know what that means. I'm going to tell you what that means. But let me first give you a short sort of history. So there will be talks tomorrow and on Thursday. You'll see that there are some recent works that now for any matroid M, we can count number of bases of M within 1 plus or minus epsilon factor in polynomial time, in polynomial of basically 1 over epsilon and number of elements of the matrix. Basically, the algorithm uses Markov chains, and you'll see about it. The question here is to basically extend this to beyond basis of matroids. So to motivate this, let me first tell you the chromatic polynomial of a graph. So if you have a graph G, you can define this univariate polynomial, which counts the number of colorings of that graph. And it's simple to define. So let's say it's a recursive definition, which just says that if this P is the chromatic polynomial, P of G X is equal to P of G minus UV minus P of G contracted UV. So by this I mean the chromatic polynomial of G in terms of the variable X is this minus that, and there's a very simple proof. Basically, like if you want to color the vertices of G with the proper color, first you forget about the edge UV, you color the remaining graph. But now you have to exclude some colors. Which colors? The colors that color U and V with the same color. That's exactly the number of colors in the graph where you contract the edge UV. Okay, so this exactly gives you the chromatic polynomial. In fact, it proves that for every x, for every integer x, this gives the number of coloring of G with x many colors. It follows from this proof that this is indeed a polynomial. So you can write it down like this: summation of ck minus x to the k. Okay. And so the question is, what is ck? This is equal to number of non-broken independent sets of size k. Okay. So in particular, if you can solve, I haven't still said what that is. I will say it. But if you can count this, we can estimate the coefficients of the chromatic polynomial of a graph.
Negative 1 to the n is missing.
What is missing?
The coefficient would be minus 1 to the n. So a minus 1 to the n is missing.
Minus 1 to the n. It's not, okay. Okay. Yeah. Okay, okay, now we can ask, okay, who cares about coefficients of chromatic polynomial? So here is one reason. So there is a theorem of Stanley that P of G comma minus 1. So if you evaluate this polynomial at minus 1, this is equal to number of acyclic orientation of a graph.
Then there shouldn't be any negative 1 to the n in front. You already had it.
Yeah.
Already with that sign.
Maybe, absolute value of this is a number of acyclic orientation. The thing is, the coefficients of this has alternating signs. So when you evaluate it at minus 1, they all would have the same sign. And if you can approximate this, you can approximate that number. And this is again another quantity which is open to like we don't know how to compute. There are other applications of this. So there's also a generalization of this. So this is just for a graph. You can similarly define a characteristic polynomial of a matroid, where here, okay, so I mean, we can similarly define, let's say, characteristic polynomial of a matroid M. It's the same thing. It's summation of ck minus 1 to the k. And again, k, this ck is number of non-broken independent sets of the matroid as opposed to the graph. So it's the same thing. That is also an interesting question. So there, if you plug in minus 1, you get some interesting quantities. If the matroid corresponds to hyperplane arrangements, it corresponds to a number of regions of that hyperplane arrangements. Okay, I don't want to get into it, but don't want to make it long. But yes, just applications is. So applications for matroid would be number of regions, hyperplane arrangements, and number of vertices of zonotopes. Okay.
You want minus x there.
Oh yeah. Yeah, so these are like some applications. Now, okay. So let me tell you what is an unbroken base. After all, so it's the following: you order the elements of the matroid by some arbitrary order. So choose an ordering. So let me definition of an unbroken base. Let me first define. Okay. So first, let's fix an ordering of the elements. So let's say 1 is less than 2, less than 3, less than n. These are the underlying elements of your matroid or your graph, whatever. Then you look at. Then we say. So fix a cycle. So fix. Okay, I mean, it's going to be a cycle in a graph, but for a matroid it will be a circuit. So let's just think about the graph case. Fix a cycle. Let's say this is a cycle, maybe with edges 2, 3, 5, and 9. So this is a cycle in the graph. If I exclude 2, so have these three elements, this is a broken cycle. Okay, so if you exclude the minimum element of a cycle, you're going to get a broken cycle. Okay, so a broken cycle is a cycle where smallest element is removed. Okay. Now, a non-broken cycle is any set which is not like that. So, for example, if I remove 3, it's non-broken. And in general, you can define a non-broken set or a non-broken independent set. It's a set that has no broken cycle. So we say I is a non-broken independent set if it has no broken cycle. Okay. So for example, maybe let's see. Maybe let's do one example. Let's say if this is 1, this is 2, this is 3, this is 4, maybe this is 5. Then you see that if you want to have a non-broken independent set, you definitely always have to include the smallest element. Otherwise, it's going to be broken. So I'm going to definitely have 1. Now, okay, for example, this is now non-broken. I can exclude 3, or I could exclude 2. Here, this example has only 1 cycle. So as long as I have the minimum element of that cycle in my base, this is enough to have an unbroken base. But if you add more cycles, it could get more complicated. Okay, so that's a definition of an unbroken base. If you have an unbroken base, any subset of it would be an unbroken independent set, and that would actually give like any non-broken independent set is a subset of an unbroken cycle. Is a subset of the non-broken base. So there's actually a simplicial complex you can get out of this. There's a whole theory about this. There's an interesting theorem, or very sort of inspiring theorem by Whitney that the number of non-broken independent sets or non-broken bases is independent of this ordering. This is a non-trivial fact, but it is true. So for every ordering that you choose, you're going to get the same number of non-broken cycles, or non-broken independent sets or non-broken bases. Again, for those of you who know Kruskall's algorithm, so output of the Kruskall's algorithm is always a non-broken base. That's the exercise you can prove. So there's always at least one non-broken base, and that's the output of the Kruskall's algorithm. Yeah, and basically the question is to just count this. There is another important connection here. So there is basically all these results on the counting basis of matrix connects to this recent developments on Hodge theory. So basically, like there are these recent works by Karim, who is here, Juni Ha, and Eric Katz, who show that the coefficients of this polynomial for any matrix is log concave. So there's a lot of interesting linear algebra and geometry going on, but basically, like one inspiring question is, can you use that fact, the fact that these coefficients are log concave, to count number of non-broken independent sets or non-broken bases of a matrix? Any question?
It doesn't have to be as polished as Sharon's talk.
I just want to add maybe a shameless bit of advertisement here. So I'll be speaking on Friday about some techniques that might be helpful to answer this question.
Okay.
I will be speaking about polynomial spaces that count all these objects.
Okay, so we're going to start with that Friday.
So I can kind of, I will preview an open question I wanted to ask during my talk, but then I have more time for something else, so I can spend more time of explaining things. So the question is essentially, to what extent Hall's theorem. Yeah. Also, is this a whiteboard or is this one?
Oh, no. You have the same. That's basically.
Okay. This is a lot of preparation. Okay. Let me. So, what does the classical Hall marriage theorem say? It's rather simple, right? We have two finite sets, x and y. There is a version for infinite sets, but I will not go into this. And there is a relation between them in such a way, and this is kind of, this is supposed to encode some kind of acceptable partners, such that for every subset A of x, the number of acceptable partners, so the subset of elements y, the subset of y of elements that are somehow acceptable or related to A and x, satisfies the following inequality, right? So this nice inequality. So, and the statement is then that if such an inequality holds, then then there exists an injective morphism, there exists an injective map from x to y that is supported on this relation. Or in other words, there exists a choice of that you can pair up the elements of x and y in such a way that x, the element that you chose in x is always related to the element that you chose in y. Right? That's a kind of simple way of talking about Hall's theorem. Okay, and so on Thursday, I think, I don't remember when, I will basically say that under certain conditions, this is true in algebraic geometry as well. And this essentially takes the form of the following object. So you have this, let's say, a commutative graded ring. So let's say A. And you want to say that, let's say, you have degree 1, you have degree 2 here. And you want to construct an injective map from degree 1 to degree 2. And you have a Hall-like condition, and this Hall-like condition says that essentially for all ideals in A, if you look at the dimension 1 component, all right, so I look at the ideal in degree 1, and I do look at the ideal in degree 2, I have this dimension inequality. Okay, so this is kind of the necessary condition for there to be an injective map from degree 1 to degree 2 that is supported by the ring. All right? Otherwise, you cannot do it. But is it also sufficient? And the answer in general is no. For instance, if the ring is non-commutative, then you can just take the cross product. Okay, so you just think of this A as just R3. And here it's also R3. And then, okay, so the cross products will be expanding in this sense, but it will not support an injective multiplication. So, okay, so this is maybe because it's non-commutative, but you can also construct commutative examples like that. So my question is, in what generality does this hold? So on Thursday, I will say that basically for toric varieties this holds. But I really have barely an understanding on when some of these expanding properties imply some injective map. Okay, that's a kind of, I don't know how basic this question is, but it sounds very innocent, but I don't see any good answer. You have questions?
Yeah, can you unpack sort of for computer scientists what does it mean? Like all...
Well, okay, so so the Hall matching theory, the Hall marriage theorem, the constructio under the bare minimum of conditions in construction a matching, right? Maybe you prefer to call it a matching. And so I prefer to think of a matching as a map, right? For every element on one side of your bipartite graph, f of a, for every element a on one side, f of a is kind of the matched element. And so the map is in particular injective because it's a matching, right? It's also surjective. And now you can ask what happens for vector spaces, right? So you have a map between two vector spaces, or a space of maps between two vector spaces. Under which condition can you find an injective map among your family? And now one necessary condition is that if you look at all the subspaces in your starting vector space and all the possible images, then all the possible images should be at least as large in dimension than your starting vector space. Otherwise, you cannot never find an injective map. So now the question is whether this is also a sufficient criterion, and this turns out to be wrong. Right? The cross product is one example.
Then you want an injective linear map between them.
Yeah, I want to really an injective map from my family. That's it. Yeah. And
it doesn't have to be linear.
It doesn't have to be linear, but somehow this is restricted to linear maps. Yeah. I mean, this is kind of commutative graded rings generated in degree 1 if you want.
The vague similarity with Grothendieck theorem, right? If you have a polynomial map between Cn and Cn.
Yeah, that's right.
Then it's surjective.
Yeah.
Do you have a guess for what the expansion property should be?
Well, the expansion property that I want is kind of this ideal, this expansion property here, right? I give you a family of possible maps, right? And you want to find an injective map among them. And clearly what is a necessary condition is this monotonicity of dimensions, right? So if you look at the subspace of your starting vector space, right? Then you have to look at all the possible images, right? Then this object has to be large enough, right? This is just a condition here, and I will basically discuss it more. Something like this is true in toric varieties, but I don't know how to do this in general.
Is there some choice of graded ring, an ideal, that will actually give you back the Hall merit?
Okay. Yeah, you can construct one, but that's kind of you can construct a finite finite version of this, and then get back called Hall merit theorem for every kind of bipartite graph that satisfies the conditions. For me, the interesting case is kind of when you have some kind of infinite things, right? So it's a kind of infinite Hall theorem that I'm looking for, but with restricted maps. That's a kind of conjecture. Okay. I think who's next?
Can I ask a silly clarification question? Mm-hmm. Suppose you just have two finite dimensional spaces.
Mm-hmm.
And then you must have some sort of relationship, right, between, subspaces of one, right? And subspaces of
this is my family of possible maps.
Right. And then you want to construct an injective map that would, so that what you get is always in the relationship that you initially had.
Yeah.
So in that generality, does it quickly become false?
It quickly becomes false. Yeah. There is an example by Kazhdan that is very nice that shows that even for polynomial rings, essentially.
So it's really important that your structure is the way you describe. Do you know any other structure where it works? Apart from the classical Hall.
No. I mean, so I will talk about toric varieties on Thursday, and David Kazhdan and I have a few more cases that always come from, in some way, algebraic geometry, spherical varieties. There are some spaces that some quotients of reductive groups that Venkatesh constructed. These are but these are very special, very rigid spaces, and there's always a different reason that somehow we can prove it. But I don't have a general understanding why this is true sometimes and why it is false sometimes. Okay. Let me go before there are more questions.
Okay, I can talk about one question, which is okay. So this is not my question. This is basically a conjecture of Dima-Shletenko, which is related to some of the things we heard about today. Quite intriguing. So let's recall the central limit theorem for classical random variables. So let's say you have some bounded random variable x, which has some density mu, it has a density with respect to the Lebesgue measure. Then we know something like if you take IID copies of x and you scale them so that let's suppose the variance, let's say the mean is 0, the variance is 1. Then we know that if you take a sum of independent copies and scale by the scale so the variance remains fixed, this converges to standard Gaussian. That's a COT. But there's actually a more quantitative version of this fact that says something about the entropy of these random variables. So we know that let's define the entropy of a measure in the usual way. So if it has a density, it's just that's the entropy. So one thing which is actually true in the central limit theorem is that as you look at these sums and you let n go to infinity, the entropy increases. So I believe Stam proved in the 50s that if you take so let's say you take 2 independent copies of this random variable, that corresponds to convolving this measure with itself. And I'm going to use this notation to mean you just rescale by square root 2 to make the variance fixed. So then he proved that the entropy of this is greater than the entropy of just mu. Okay. Proving that this is actually monotone in n was open for over 50 years. And there's a paper of Artstein, Ball, Barta, and Naor from 2004, which actually proves that if you look at the entropy of these sums, then this is monotone in n. So as n gets bigger, this entropy actually increases. Okay, so what I want to talk about is so maybe before that I should mention there's an analog of this in free probability, which we heard a little bit about today. So there's an operation called the free convolution. Okay, so it takes 2 measures and spits out another measure. I won't redefine what it is. It's some different notion of independence. It's a different. There's a quantity called free entropy, which is defined by Voculescu, which the appropriate definition is it's a double integral of log x minus y t mu x t mu y. And this looks kind of weird. It doesn't look like it's so related to this, but this is actually a log of a volume of something. So it's a legitimate, it has a lot of the properties that entropy has. And there's a result of Shletenko from 2005, which proves that if you now play the same game but with the free convolution, it's still true. So you look at the free convolution of some compactly supported measure, and you look at the free entropy, this is also monotone increasing in n. And in this case, the appropriate limiting distribution is the semicircle law, which maximizes the free entropy subject to variance. Okay, so Shletenko's conjecture is that the same thing is true for finite free convolution, which is what we saw some talks about. So that's classical, this is free. So what's finite free convolution? So if you have two polynomials, let's say they're characteristic polynomials of some matrices. So this is a characteristic polynomial of diagonal matrix A. This is a characteristic polynomial of some matrix B. Then you can define the finite free convolution. So let's say these are n by n matrices. N by n real diagonal matrices. And you can define the free convolution as the expected characteristic polynomial of A plus Q B Q transpose, where Q is random orthogonal matrix. And we know that this has real roots. Okay. So what this does is this gives you an operation which takes two discrete measures on n points. That's what a polynomial of degree n is, and spits out another discrete measure on n points. And now you can mimic this and define a notion of entropy for a polynomial. So what's the definition? Let's call it h sub n of a polynomial. Well, this is a double integral. I'm just going to take it to be a double sum. So it's a summation over pairs of roots ij log of lambda I minus lambda j. And there's some normalization factor 1 over n minus 1. Okay. So for a polynomial p which has roots lambda. Okay, so it's like a discretization of this entropy quantity. And it's actually a natural quantity from an algebraic point of view. It's just up to this normalization factor. It's just log of the discriminant, right? Because that's all it is. It's log of the discriminant of p up to some normalization. And so Slaktenko's conjecture is that this quantity is monotone with respect to the finite free convolution. So the baby cases of it, forget about the n thing, which was relatively hard to show even in the classical case. Let's say you take two polynomials and take the finite free convolution. Well, that's going to increase the variance of the roots. So you have to rescale everything to make the variance small. And the right thing to do is to divide the roots by square root 2 again. So, and the conjecture is this is increasing. Okay. I mean, we checked this experimentally. It's true. We know how to prove several special cases of it, but there's no. I mean, I'm quite sure this is true, but the problem. I mean, in all these proofs, if you look at all these proofs, you have to somewhere use the fact that these measures come from random variables in some sense, and the random variables can have things such as a joint distribution. Here, this is a very elementary statement about discriminants, essentially, of polynomials. But we don't know how to define random variables in this context. We just have these discrete measures. So this phenomenon is probably some shadow of some interesting thing that's happening, but we don't know. I think we're just lacking the definitions to prove something like this. But if you can, I think you'll find some interesting new definitions. And I should mention that this is. So, I mean, there's a version of this for two different polynomials, but if you only care about real rootedness, this is actually saying something interesting about real rootedness. The discriminant is a measure of how real rooted a polynomial is. So recall that the boundary of the set of real rooted polynomials is polynomials with double roots, which have discriminant 0. So what this is saying is when you do this convolution operation, you make the polynomial more real rooted in some sense. And yeah, so that it's also interesting from that point of view. But anyways, conjecture is due to Slaktenko.
More real rooted, but probably also means that the roots repel, right?
Yeah, so it's articulating the fact that the roots repel. That if you have some polynomial that already has some discriminant, when you apply, so Jonathan mentioned that, I mean, okay, there's a version of this for two different polynomials, and Jonathan mentioned that all linear transformations preserving degree and real rootedness can be written like this. So what this would be saying is that if you apply a linear operator that preserves real rootedness for degree n polynomials, the roots repel in some concrete sense related to the discriminant.
So we saw there submodularity inequality for such convolutions, correct?
Yeah.
Would that be useful in this context to see what the discriminant actually does under this operation?
So that's a good question. So there's submodularity inequality is a statement about the largest, I mean, okay, it's not true. It's a statement about the Cauchy transform of the roots, but it's, I mean, the way it's used is usually just to reason about the extreme roots. It's not very sensitive about the spacings of the roots on the inside. You don't expect the Cauchy transform to care about the delicate details of the spacing of roots on the inside. This conjecture is some statement about the global spacing of roots inside the
This is also an aggregate statement. This is not super delicate about specific.
That's right, but this doesn't pay special attention to the extreme roots. It cares just as much what happens in the interior. Whereas the Cauchy transform is really something that's concerned with, I mean, puts a lot more weight on the extreme roots.
Is anything known about what the discriminant does under this convolution?
Yeah, I mean, for specific cases, things are known. Just this is not known. Most of it is not published, so I don't. I mean, I know several people who have results about this. I don't know whether I want to cite them, but nothing nothing in general is known of this.
Yeah. Is it known if you just get rid of the root 2?
Yeah, it's easy if you get rid of the root 2. Yep.
So what happens if you take a unitary group instead of the orthogonal group?
Yeah, so your question is if you replace this with unitary, does it change anything? It does not. The polynomials are literally the same. So you can do orthogonal, unitary, or even signed permutations here, and you get the same thing. So it's different from the Yep.
So do you know anything when P is Hermite?
Yeah, okay. So we know how to prove this when, okay, there's a version of this for two polynomials. We know how to prove it when one of the polynomials is a Hermite polynomial. So that's one of the special cases. That's, yeah, something we worked out with Dima and Adam. That corresponds to proving this in the case when one of the, you can ask this question, what if one of these things is Gaussian? That's relatively easier to prove. So we can prove that.
What happens if you have complex rooted polynomials? Does this still hold?
What happens if you have complex rooted polynomials? I have no idea. So yeah, I guess everything written here makes sense for complex rooted polynomials. I don't know. Good question. It might, yeah, maybe it's true for complex. Okay. Any other?
That's a quick one.
Yeah.
Pretty obvious what this has to do with this conference, and I've asked this question before, but I'll ask it anyway.
Okay, so let's say you take a random word, uniformly at random, where like the symbols in the words are the numbers between 1 and n, and it has length d. Okay. So like a random string. And then let lis of w denote the length of the longest increasing subsequence in w. And increasing means non-decreasing. Then I'm interested in the expected value of LISW. So let me first say a lower bound. Whenever you have a string, you can get a non-increasing or a non-decreasing subsequence or an increasing subsequence by just taking all the copies of 1. Or you can take all the copies of 2. Or you can take all the copies of 3, etc. And one of these will have length at least d over n. So in fact, the longest increasing subsequence will always be at least d over n. So the expectation will be at least this. So it turns out, this is something I proved with John Wright. We were studying a problem in like quantum learning. We proved this. It's not too much bigger. It's not much, it's bigger by at most 2 times square root d. So let me just now, you might say, what's the open problem? Because that's the answer. I'll just say a couple things to intrigue you. First of all, the open problem is to prove this without using representation theory, which was how we proved it. And just let me add about a comment. This 2 is like the 2 comes from like the edge of the Wigner semicircle distribution. So that's why it came to my mind for this conference. It's even kind of entertaining to prove this when capital N is 2. That I know how to do with combinatorics. So it's a random binary string. Okay, that's the whole question. Are there any questions? Yes?
Why would you like to prove it without representation theory?
I don't know, wouldn't you?
Yeah,
I mean,
is there more?
What's that?
Is there more? Is there something else you could maybe do then?
You could feel like you know why it's true if you're a person like me, as opposed to like be able to follow some calculation that maybe your co-author worked out. Oh, thanks. Is there another open question? I'll ask.
Good. Well, I guess that's it. Well, thanks a lot.